record on this computer. And I guess we're moving a little bit in chapter 5. This particular lesson centers on pulleys and tensions in cords and cables. And of course, we've talked about that before. Much like Monday, we talked about friction. But we talked about friction before. We just came up with a way on Monday to calculate static and coefficient of friction. Today, we're going to do problems that contain pulleys and tensions. We've used them before, but now we're going to think a little bit more in more detail about them. And so any questions on anything that you read, watched in a video, anything like that? All right. Give you a second there. Okay, it doesn't look like anybody's putting a hand up or anything. So I'm going to just start sharing my PowerPoint so we can do a little bit of polling like we often do. All right. Where's my poll button? It always hides what I want. There it is. And get to the right one. This is 541. Launch the poll, and you've been seeing hopefully on my screen the elevator is slowing down as it approaches the desired floor. And true or false question: the MA force can be added to the normal force or the weight of the man. And by the way, this is exactly the worksheet problem from I guess last Friday. It was 5.2, worksheet 5.2. All right. So we got 22 of the 26 people in, 24. All right, we'll end it and I'll share it. And this is kind of consistent with what I'm seeing as I'm looking at the work you're doing. Okay, it is one of the reasons, by the way, that I believe in my looking at your worksheets to see the work you're doing as opposed to mastering physics, where you put a number into a computer and I have no idea how you got the number. Because in my opinion, and some of you may think I'm kind of wordsmithing maybe or splitting hairs here, I agree with the 8 of you who said false. MA is not a force in and of itself. In our category of forces, we have normal forces and weight and tension and friction and thrust from like a rocket. Oh, I'm gonna choke on the rest of them here, but I got 5 off the top of my head. Spring forces, both in tension or compression. That was a 6th. If you can think of the other one, that's great. But those are the things that we can add up in Newton's laws, right? We're not allowed to add up MA. We add up a number of forces, okay? Some people like to write instead the net force. Those are the things we can add up. That sum, that net force, is then, look, there it is. Oh, it's auto-saving. Great. Is equal to MA. So some of you are saying, well, ultimately you do combine it. You combine MA with the forces. I don't disagree with that. Algebraically down the road, that's what's going to happen. But strictly speaking, you don't add MA as a force. MA is the result of a force. The very concept of Newton's second law is lost if you think you can just add it to other forces. Newton said that the net force results in an acceleration, and that acceleration is proportional to that force and inversely proportional to the mass. Okay, so MA is not a force to be added. It is the result once you're done adding. And I think if you accept that as a paradigm shift, maybe, I hate those words, but that's what people used to say about 10 years ago, you'll be more successful in physics, and that could be the difference between that B grade and that A grade for you. And so when I'm looking at this elevator problem that was on the worksheet that I graded last night, I finished grading them up during that horrendous debate. I thought both sides were acting like just idiots. I didn't think the moderator did a good job. That's another story, another day. But you look and you have the person here, and there are forces acting on him. Okay, normal forces up, weight forces down, and in this case, the elevator is reaching the top floor and slowing down. And so the motion diagram would look something like this. And so that means an acceleration downward. That's why I drew a downward acceleration. And if I look, that must mean that the normal force, I should go lowercase n because that's, if you put uppercase n, I'm fine with your notation. Some people like force with a subscript n, that's fine too. But it's normal force minus the weight force is equal to, see, those are the things I can add. That's the point of my problem. The things that are in the free body diagram are the things that I can add. That is equal to mass times acceleration. Now, there's a problem here. What I wrote is not true right now because I made the normal force positive, right? Didn't write it, it's implied. There's a positive sign right there because it was upward. I made the weight force negative when I added them, okay, because it was downward. And look what the direction of my acceleration is. According to Newton's second law, that must be negative as well. Okay, and so now you're done with drawing a free body diagram, which has to happen in virtually every physics problem in chapter 4, in chapter 5. We're going to start chapter 6 on I guess Friday, and continue on that. And then chapter 7, we're going to talk about rotational motion, and we're still going to have free body diagrams in chapter 7. At some point, we'll start talking about energy, and I forget if that's chapter 8 or 9. And then energy is a scalar, so drawing a free body diagram with vectors isn't as applicable. You might still have to occasionally, but for the near term, you got to be able to draw a free body diagram, and you got to do it. That is part of the correct answer. Okay, and then you got to write the sum of the forces, the net force, whatever notation you like, write either one of those things and set it equal to ma. And then you got to look at your free body diagram, and you have to add the forces. And sometimes it's forces in the x direction and the y direction. And you got to set it equal to the mass times acceleration. Then you got to do a consistency check that all the vectors that are in the same direction have the same sign. And then, finally, then you can go about and solve the question, which I think in this case, you were asked what the normal force is. Well, once you got this, okay, then you can go, well, a little bit of algebra. Just bring the weight to the other side of the equation, and it's weight minus ma. Okay, and this may be why people think I'm splitting hairs. Ultimately, right here, when you get to the bottom line, yeah, I am taking the ma and I'm subtracting it off the weight in order to get the normal force. But I saw a lot of people thinking that this was the first thing you should be writing down on your paper. And I think I may have told you about the movie Good Will Hunting and pop culture idea of how you solve STEM type problems. And Matt Damon's vision as he's relating it to his girlfriend in that movie is, I just see it. And that's what people who write something like this down as the first step in a problem, I just see it. Well, it's a 50-50 chance whether you're going to make that as a plus sign or a minus sign. And this is one of the things I recognize about mastering. You get multiple choices. So you go with a plus sign first, you get the answer wrong, you switch it over to a negative sign, you get the answer right now, and you're off. I would tell you, and this is that definition of insanity, if that's your method and it's not necessarily working, getting you the desired result you want, like on a midterm grade, it's time to change your method. Otherwise, you're meeting the definition of insanity. You have to not just get the answer right so that the thing turns green and says correct. You got to be able to do it correctly on the next exam or on a quiz or on a final or something like that. That's the test for you to really have it. Now, if you're not buying anything I told, and believe me, I've been doing this long enough that I know this is a hard sell, okay? That in order to get this problem right, you don't just start with this equation in the box here. You go through all this rigmarole I'm showing up at the top. That's part of your solution. For full credit, I said on the first midterm, you must show your work. Just so there's no ambiguity, I am talking about a free body diagram. I am talking about a statement in Newton's second law. And then I'm talking about a sum of the forces. And then I'm talking about a little bit of algebra to manipulate these forces. And sometimes the algebra is intense. Sometimes it's 2 equations, 2 unknowns. And then you arrive at a result. And then finally, if they're numeric values, you plug in the number and you get a numeric result. And it should not be too difficult to accept that. Although, believe me, if you're resisting, you're not the first. If I was to give you if I was an algebra teacher, I don't know, 9th grade, whatever you took algebra, maybe some of you took it in 8th grade, and I give you that equation right there, that quadratic, x squared plus 8x plus 12 is equal to 0. would your first step, and I said solve it, okay? Would your first step be to write x is equal to? And it may be. There's one case. And so that's what people are doing in the physics problem. You're told find the normal force here, so people write n is equal to. And then there's an equation hunt, right, where you try to find the one equation that will allow you to get that. And if you know the quadratic formula, minus b plus minus the square root of b squared minus 4ac, all that over 2a, if you know that, well, then that is the way you would do it. But more likely, most people would look at this and go, well, I got to do some manipulation on this thing, some algebra. So you'll say, we'll factor it, right? We'll go, well, let's see, what two numbers multiplied together give me a 12, added together give me an 8? 6 and 2. So you'll write something like, must be x plus 2, x minus plus 6. I guess it could be minus. No, it couldn't be minus minus. They have to all be plus here. Okay. And that's the check you're doing as you're writing this, right? You're going, okay, that has to be true. And I usually check it, x squared plus 2x plus 6x. There's my 8x plus 12. Yep, that works. And that must mean then that x is equal to minus 2 minus 6. And so in an algebra problem, which often a physics problem is, it's an algebra-based physics course, you have to work through a problem, not expect to have x is equal to, and then fill in an equation, okay? And for full credit, that's what you have to do. You have to show the work. You have to, if it was an algebra class, you'd have to show that step. If that step's missing, even if you get these numbers right down here, okay, unjustified, you don't get full credit. That's kind of the way the game's played. All right, enough. I just wanted that this is what you have to do. And if you want to be successful and get the answers right, this is the method, okay? There are people who will say, I can find a better method. There is a better one. This type of physics has been around for literally 400 years. You may be able to find a better way. There's been a lot of physicists that were geniuses that have not figured out a better way. My advice is to just do it, okay? Just do it. All right, moving on to the next one. And I guess we'll see if you believe right here based on what happens with this problem. Stop sharing, move on to the next one. You can read it there for a second. That's not the right one. 542, there we go, launch poll. And so the question, I guess, on the tension, which is in that cord, we're talking about pulleys today, there is a pulley. Is the tension less than, equal to, or greater than the weight of that mass? And about 6 or 7 more people to vote here. Draw that free body diagram. Look at the sum of the forces. Make your determination. You don't need to just see it. There's no requirement to do that. All right, one more person. I'm going to end the poll, share the results with you, and tell you I didn't sell my argument to you. I clearly failed. It's all right though. I don't know if I've mentioned about my kids. My youngest is 33 years old, so I took. I've had kids not listen to me, including my own, for years. It doesn't hurt my feelings. I just kind of feel bad because I'm trying to give you pearls of wisdom here. The reason that 15 people got this problem wrong, I think, is because you didn't look at the free body diagram on that mass and identify the two forces acting on it, the weight and the tension. And let's see, it says the top block is accelerated across this frictionless table. So there's your acceleration. And if that thing's going that way, then the mass must be accelerating downward. One of the key points of today's topic is that since that cord isn't stretching or anything, those two accelerations are the same. And then you look at it and you go, okay, what's the sum of the forces acting? Question? Acting on the mass, and the sum of the forces, it's in the y direction. Tension up minus weight, and then that's going to be equal to Those are the forces I can sum, right, to get the net force. There's only two this time, so it's a pretty easy sum. That's equal to mass times acceleration. Okay, and then you do the consistency check. This is up, made it positive. This is down, made it negative. Oh, the acceleration is down. I should have made it negative 2. Okay, and then you look at the tension, and weight is, of course, mg. You solve for it. It is mg minus ma. Okay, so no, not true. That must mean that the tension is greater than the weight. Well, how much greater? By the mass times whatever the acceleration turns out to be. That's how much greater it is. So the three people who went with, I'm sorry, tension must be less than, because it's a negative sign. The 10 people that went with this one, you got it right because of that negative sign right there. Because of the direction of the vector right here in Newton's second law, which came from this free body diagram, and just a reminder to yourself of what direction the acceleration is. Okay, and so the answer is A. And there's a better free body diagram, I suppose, if you want, although it's not free. Tension has to be less than the weight. Otherwise, it wouldn't be accelerating downward. There would be no net force. If they were equal, there would not be an acceleration because there would be no net force. They could be at rest. They could be moving. It could be moving at constant velocity. That would be the requirement for B. All right. Draw your free body diagram. Look at Newton's second law. Sum the forces. Then do the algebra and solve for the thing that you're asking. It's a royal road. Got to take it. All right. We'll stop sharing that one. And the last one for today. Oops. Sorry about that. Hit the wrong button. We'll see if you saw it or not. And I'll move on to the next one. But the argument still has to be there, even if you can get the answer right. What's your argument? All three docs are at rest. Yeah, people in quick. And again, free body diagram. The pulley side is a little bit difficult conceptually to think about. Yeah, hit the wrong button. Everybody's getting it. Or I made you believe. Who knows? Remind you what my calculus teacher used to scream at us when I was, I guess, a freshman, calculus 2. A man convinced against his will is of the same opinion still. Obviously, that needs to be refined for this millennia, but he was right. All right, 25, couple more last people. Yeah, okay. We'll stop, end it. I'll share the results with you. And again, look at the free body diagram, and that's sitting right there. Okay. And if you look at free body diagram 1, we've got a 50 kilogram mass. The weight and the tension in this case are equal, right? Okay. So whatever the weight is, it'd be about 500 newtons if G is about 10. And, in your mind's eye, that's a good way to just kind of check your numbers when you put in your calculator. Make G 10. It's about 500 newtons of tension in 1. And then in 2, the free body diagram, oddly for both masses, is the one that's drawn here. Okay. And we say that in a pulley, the topic for today, those two tensions are the same. All the pulley does is redirect the tension. Okay. It's up here and it's also up here. Okay. Normally, if you have two masses connected with a string, right, one pulls that way with a tension, one pulls that way with a tension, and the string would be right there. Okay. They're in opposite directions. The pulley kind of redirects for us. So in this case, they're both up. That's what pulleys do. And at this point in the course, until we get into, I guess, chapter 7, that'll always be a fact for us, so we don't have to do it. All right. Any questions on anything we did today? I'm hoping that it wasn't because I showed you the answer why most people got it right this time. I'm hoping free body diagrams entered in, but I guess we'll see. And so I'll stop sharing this, and I'm going to move over to what we're going to be doing next. And I managed to get through, even with my pontificating, I got about 10 of, so we've got about a half hour, and I've got 2 problems that I want to be worked. Let's see, I want to share. Yeah, there they are. Share screen. Where is it? All right, I don't see it. So let's try one more time. Hit the share button. All right, I don't see the border, so I'm going to stop sharing and try it a third time. Maybe third time will be the charm. Acrobat, share. There it is. Now I see a green border. So you may have been seeing it before, but it wasn't giving me the indication. So here's the two problems. You can see a pulley and, of course, an inclined plane. We can always combine, and we're giving you the mass of the two blocks. We're telling you that it accelerates upwards, and we want to find what that acceleration is and what the tension is. We also give you the angle of that inclined plane. Okay, so half of you are going to work on this problem. And then the second problem is not an incline, but in this case, there's a coefficient of friction between block one and the surface it's sitting on. And you got to kind of expand out the surface. Block one is able to move a little bit longer. This is going to be the lab next week, so it's a good problem to do. Although the lab we won't be considering friction. Okay, so again, you've got two blocks. We tell you the mass. We tell you the coefficient of friction. This thing that's a circle right here is a pulley, and we again want to find the acceleration of the system and what the tension in the cord is. Okay, both answers. Now, one of the things I've been noticing is when we break up into groups and I'll pop into a group, I'll find dead silence. And I've been told by two people, and whenever two people tell me something, I have to assume that there are more, is that they get into you get into the breakout groups and nobody talks. Okay, and I kind of get that. I don't know how many of you have studied psychology, but if you've taken that course, one of the things you recognize is or maybe you've studied in a course like that, is the Myers-Briggs personality survey. And it's very possible that some of you have, for your first attribute, it's introvert, extrovert, intuitive versus sensing, thinking versus feeling, and judging versus perceiving. Those are the four attributes that they look at, and they consider each of those as a spectrum. So you kind of put people into a four-dimensional personality space. And the first one, introvert and extrovert, it isn't about social interaction. It's not about, how are you the life of the party because you're charismatic extrovert. No, it deals with how you approach solving problems. And the introverts like to be left alone in a nice quiet space to work a problem. And if that's you, that I understand completely. You're going to go into a breakout group and you're going to want everybody to shut up so you can do your job. And I completely understand that. Whereas the extroverts, okay, they want to talk the problem out before they move on. And sometimes just in the talking out of the problem, they're able to see a solution that they might not have even been able to see just thinking about it themselves. Both methods are perfectly legitimate, and I don't want to force anybody to do anything, with the possible exception of, since this is a college experience, if you are more comfortable being an introvert, well, maybe try being an extrovert, try working problems out vocally. Sometimes I find when students are coming to office hours, I just ask them to explain the problem to me, and as soon as they explain it, the answer comes right into their own mind. And that's the value of being an extrovert. You're going to get plenty of opportunities to be an introvert, right? Because that's how all the exams are going to be. You're going to have to do those yourself in a nice quiet space. And so you get an opportunity to do both here. Anyway, so here's the thing I want to do. Well, we're down to 25 minutes now. You're going to get 20 minutes to do each of these problems. Okay. In the last 5 minutes, I'm going to pull everybody back. Right around quarter after, I'll pull everybody back. You could send me a chat message from your breakout room. And what I'm looking for is somebody who wants to show their solution to the rest of the class. And the motivation for doing that, if you're so willing, is you can have 5 points instead of the normal 4 points. So you get an extra credit point. And then you also don't have to upload the solution by Friday. If you don't want to do that, that's fine. You upload the solution by Friday, and you should be good to go. So any questions on what we're doing? I'm going to put you into 8 groups. It'll be 3 or 4 people in each group. Half of you will be working problem 1 at the inclined plane. Half of you will be working in the other group and the other problem with the friction. And so I'm going to create 8 groups here. Here are the groups. In breakout room 1 is Aiden, Cora, Jalil, Rachel. Breakout room 2, Shenyi, Eberici, Kyle, Olivia. Breakout room 3, Emma, Nina, Shanice, and Stephanie. Breakout room 4, Kristen, Katie, Sam, and I'm going to get that. Hopefully I got that right, Mr. Wang. Any event, so you 4 are doing the first problem, you 4 groups, what is that, 16 people. The rest are doing the second problem with the friction, okay? My first advice to you, open up the whiteboard in your room and draw the free body diagram for the problem that you're working. And in fact, in each problem, I think there's gonna be 2 free body diagrams. All right, opening all rooms, have fun. I'll be jumping in and out. Please let me see a whiteboard when I show up in your room. And hopefully, once you get the problem right in 20 minutes from now, volunteer, you get extra credit point. Have fun. Bridget, you're still here. Chat. Okay. Dead silence.
Okay, so, oh, sorry, what?
You need me to give you permission to open?
Yeah, we were trying to figure out how to open the
okay.
whiteboard.
There, I may have to do that. Security. Come on. Security. right. Can you guys see the whiteboard?
Yeah.
All right. That's what you can. Somebody try and draw on it.
I cannot see the whiteboard.
I can't do all of it.
Sean, you can see it, you said?
Oh, there we go. I can see it now.
Yeah, it just meant there's a time lag in about a minute or two. All right, so there's your block 1. There's your block 2. And I guess the answer is going to come from a free body diagram that appears for block 1 and block 2. You guys are doing the second problem, right?
Yeah.
So what are the forces on block 1?
I need to go back and look at the picture.
Friction.
Friction, yeah, because we said friction. I think going to go that way because I expect everything to kind of move that way here. So force of friction. What else?
Tension.
Tension. Looks good right there. Make it T. What else? 2 more. And the other 2 only matter for the friction, I guess.
The weight and the normal force.
Weight and the normal force. So there's the weight and there's the normal force. All right, I've sketched the first one. Somebody else draw the forces on block 2. What you have to do is go to annotate, which for me is under, where's annotate? It just comes up for me, but you may have to go under the dots and sometimes it's hidden in there. And then you'll get a little pen and you can just use your mouse, draw a line.
Okay.
There you go. Look at that. What's that going to be? Yep, there you go. And tension. Yeah. Now, the one thing I would tell you, the 2 weights are different because the masses are different, right? So you might want to subscript, and maybe I should have right here subscripted mine with 1 and yours is 2. And that just reminds you that that's M2G and that's M1G, right? All right, so you got the first step done. And now some of the forces on each block, get the friction force from the normal force. Some of the forces in the x direction over here is mass times acceleration. Some of the forces here is equal to mass times acceleration, just like we did before. I'm leaving you guys alone now. You're on a roll, though. Keep going. And if I can find the button to jump out. Where's the breakout room?
Okay, so would it be does F
All right. All right, can you see my whiteboard? Is anybody alive?
Yeah, I can see it.
Excellent. All right. So there's your inclined plane.
Did you? I was working on one like.
There was one here already? I didn't see it.
Well, I don't have a whiteboard, but like I like.
Well, it's part of Zoom though, isn't it? If you go share, hit that green button that says share, it's usually on the top row is something called whiteboard. That's all I did.
Oh, okay. I usually do my problems on like Google Docs because I can like my laptop, I can write on it.
Okay. Yeah. What app are you using then?
Just Word.
So you should be able to go hit the green button again, and Word should be one of your options. You can share that if you want to, and then you can use the pen in Word. That works perfectly fine. That's what I do sometimes. Okay.
Do you
can
want
you try and share that right now?
Okay.
It takes a second in breakout rooms for some reason.
Okay, can you see it?
Here it is. Yeah, absolutely. Can everybody else see? Is this Katie? Yeah. Everybody see Katie's screen?
Yeah.
All right.
I don't know how right it is. So.
Yeah. Well, I'm gonna help you here, I guess, if I can. Shouldn't the normal and the tension be perpendicular to each other? Yes, I think the normal force, and I'm see if I can get my pen on this for you. Where's my annotate? view options right there. Under view options, I can annotate. Yeah. So I think there's your inclined plane, right? And that's why you drew the tension parallel to it, because it is the normal force. Come on, draw normal would be right there, not right there. Okay. Yeah. And so I think a good coordinate system here, make that X and that Y. And then let's see, now all I have to do is get two components of weight. That's the Y component of weight right there. And the X component, that's a lousy looking vector right there, but there's the X component of weight. And I think the angle of the inclined plane, I'll help you out with that, is 30 right there. Okay, so you got to use a little bit of trigonometry on the weight, which I think you know, right? Because you know the mass of that block is, I think, 20 kilograms.
Mm-hmm.
So that means you know that the weight is equal to 20 kilograms times 9.8 meters per second squared. Okay, and what is that? It's about 200 roughly, 196, I think. And the only reason I know that is because I've done it enough times and it's sitting right here in my paper in front of me. Okay, so that's your weight. And then to get the Y component, I'll help you with that. Which trig function though? Can you tell me? Which trig function? It'll be either sine or a cosine, right? It'll be 196 newtons times, is it the adjacent side or the opposite side of that 30-degree angle?
Cosine.
It's cosine because it's the adjacent side. So times the cosine of 30. And then you got to do the same thing to get the X component. And then you can write the sum of the forces is equal to mass times acceleration. Tension minus the X component, that's an X right there. It's important because I don't want to make it look like a Y. And it has to look like an X. All right, good to go. That gets you going. You're on the road here. I'm going to leave you guys.
Thank you.
You bet. All right.
I don't know how to make this so that I can write in it again. So I'm just gonna make a new one.
Yeah, I think it's under view options, try.
View options?
And go annotate, I think. Do you have a view option at the top?
No.
Okay.
Oh,
I don't know what to tell you, but it looks.
that's
Everything
okay.
looks.
I'll just write a new equation.
Yeah. Okay. All right. Your normal force, your tension force look good. What do you know about you? You subscripted the two tensions as something that were different. Are they the same?
Yeah, they're the same.
They're gonna be the same.
So I
Okay,
guess
that's fine.
you don't need a subscript.
Okay. Yeah, everything. Let's see. Everything looks good there. Keep going. I'm gonna leave you guys alone. You got it.
And the
Tension
acceleration
minus
is
1 minus
positive.
weight x. Oh, well.
Yeah, it's positive.
And you said weight x is sine. I agree. I think you're missing an m right here. Right there. Isn't there a mass? So it's m times g times sine of 30 degrees, right?
Yeah.
Yeah. And that's no problem. It's you didn't factor it out. You expanded over both terms right there. Good. All right. Yeah, keep going. You're almost there. And I'll leave you guys.
Okay, so let me see.
Does this look right so far?
Yeah, I'm just taking it in here. Okay, the one thing I don't see on, and I'm looking at your equation, I'm trying to figure it out. You do talk about a coefficient of friction. Isn't there a force right there, which is the friction force?
Oh,
And I think
Okay.
it's kinetic friction. Okay.
oh,
And so then, yeah, I'm a little worried about this. Okay. Because which direction, which part, which object is it? Anytime I see two things added together, that means you're trying to do some kind of composite. And I don't think that works real well. So what I would say is this guy right here, the sum of the forces, and it's on, this is on 2 here, and they're only,
would they have this?
go ahead. And you may have combined something or tried to do something else, but I would just say the tension on that guy minus the weight. Now that's mass 2, right? Which is different from this guy, which is 1. So what you're calling the force of gravity on 2 is equal to, now which way do you think this is accelerating?
Down.
Down, yeah. So it's going to be minus ma, right? And so that means tension minus m2g, because that's the weight, the force of gravity, is equal to, and I should be specific here, that's mass 2 that I'm talking about. You got to work locally. If you try to combine into one equation, it doesn't work real good. So that's one thing I know. The other thing I know over here is, let's see, the tension minus the friction force is equal to, in this case, mass 1 times the acceleration, right? And I didn't write like I did previously because it was in my mind, but I'm looking at the sum of the forces on object 1, and I went in the x direction, and that's going to be equal to mass 1 times the acceleration. And so this is what you get out of that. Now, the problem, of course, is you don't know what the friction force is, right? But I think you can look and see this way, what's your normal force? Because remember, friction force is equal to the coefficient of friction, and it's kinetic here, times the normal force. So if I can figure out what the normal force is, because I think it's exactly in this problem equal to the weight of that mass, okay, then I multiply it by the coefficient, then I've got a numeric value for this thing that I can throw right in there. And if you look, I think these two things that I've got a box around are a system of equations where you don't know the acceleration, you don't know the tension. That's a 1 right there that I crossed out. And over here, you don't know the acceleration and you don't know the tension. But the two things you don't know are both in the two equations you've got. So you can take two equations with two unknowns and solve for it. It's a pain in the butt algebraically, but you can do it. Okay. So that's what I would tell you to do. I would avoid ever, and I know you may have had a high school teacher that said, well, there's kind of a composite sum of the two masses. That limits the number of problems you can do. It may work in certain cases. You may even get the acceleration. I can tell you this is not the right acceleration, so something went wrong there, but I can't follow it. It's a little bigger than that, not much. It's 1.2 meters per second squared, but I would not take this approach, even if a previous teacher has told you that way. It solves certain problems, but what you can never get out of that is what's the tension. And so that's, even if you could get the acceleration correct. All right, I'm gonna leave you all. You can keep going on that. It's about time to call everybody back. All right, anybody in this group of groups want to present their problem? Extra credit point. Everybody's a little shy. Yeah, welcome to my world.
I can present it, but I don't have the whiteboard.
What were you
up? We would break out room 8.
Okay, You should be able to share. You guys were using, oh, the whiteboard went away on you when we came back?
Yeah, so we both just worked it out on our own paper, so I don't really know how to
Yeah, okay.
show people.
Yeah. Other than taking a picture of it, there's probably no way to project.
Yeah. I mean, I can say my answers, but I don't really, I
Okay.
can't really show my work.
I'll tell you what, tell me, so you were group 8. What'd you get for your acceleration?
Negative 5.88 meters per second squared.
And I
Is
don't
this for
agree.
problem one?
Oh, problem 1?
Is that what you're talking about? I just got in.
I think she's talking about, she was group 8, so she's doing problem 2.
Okay, got
And so I think that's a little too big for the acceleration. What'd you get for the tension?
Oh, okay. I got 78.4.
Yeah. Both of those are too big, which probably means you added something when you should have subtracted it. So there's probably a negative sign somewhere in there. Okay.
Okay. Yeah, I'll relook at it.
Look for something you might have added when you did the algebra. You probably added something on when you should have subtracted it off. The numbers I got were 1.2 meters per second squared for the acceleration in problem 2, and the tension was about 43 newtons. And so those seem your numbers look proportional to that, but I suspect just an algebra mistake somewhere. Anybody from problem 1 want to talk?
I can talk.
Can you show your solution real quick? We got about 2 minutes, I think.
I can like hold my paper up to the camera.
All right, we'll give it a shot.
Our whiteboard went away.
Yeah, that's a technical issue. I can tell you, some of the groups were working in Word and just writing on that, and then you would have that as a persistent thing. It's too bad that we all learned that Zoom whiteboards go away when we lose the breakout room. That's unfortunate. There's got to be a technical way around that. We'll figure it out. But I am happy for the groups that I visited. I only got to 4 today. I'll get to the rest next time. Doing good, okay? Even if the question wasn't being done right, working together was great. Yeah, go ahead and try showing it to your screen.
This is my free body diagram.
Right? Free body diagrams look pretty good to me, okay? Pull it up a little bit.
And then this is the equation that I wrote for the mass 1, and then the equation for mass 2 is over here.
Okay, hang on, give me 1 second to catch up here. All right, keep going.
Okay, and then our groups got solved for tension in both equations because they're equal.
Yeah, and I just want to point out, see how much algebra she had to do? There's what, 1, 2, 3, 4, 5 lines. And see that negative sign there for group 8? That you may have had that positive right there, just a little algebra mistake. And she gets 1.96 meter per second squared. And that is the correct answer.
For acceleration.
Yeah, I'm sorry, for your acceleration. What's your tension then?
I think 59.
Yeah, and all you do once you got the acceleration is you pick either of the equations, and I can see they use the one from the Y, right?
Yeah.
And just plugged it back in, and you got 59 newtons. Who else was in your group?
Nina, Shanice, and Stephanie.
Nina, Stephanie, Shanice, and you're Emma. All right, you guys get the 5 points. Hey, for the lab, if you're coming today, I'll be going over the exam. 1:30 is today's, I believe. I'll check the time on that. Just use the normal link for Zoom for coming to class, and that's where I'll be at the start of the lab today for anybody who wants to go over the exam. Okay, any questions? Hey, good job on working it. Make sure I got that. It was Nina, Stephanie, Emma, and who was the third person?
Shanice.
Shanice. Sorry, Shanice. You got it. All right, you guys get 5 out of 4 for that. Good job. We'll see you all on Friday or at the lab before going over the exam. Have a great day.
I have a question.
Sure, go ahead.
Will you have coach class today at 10:30? Because the friction problem, I kind of that was due today. I kind of have an issue with it, and I was wishing like if you could go over it.
I have to go to the dentist right now.
Okay.
What time? When is it due?
It was due this
It actually
morning.
doesn't matter because it's just Canvas, and so it's due whenever I get done grading it. So can we talk this afternoon, like maybe 2:30? Are you available then?
Yeah,
Right.
no problem.
Yeah. So what I'll do, I think, let me check to make sure. Lab is. Are you in today's lab?
I'm with the Dr. Chem group.
Yeah. Are you in
So-
Dr. No.
Yeah.
You are in Dr.
Yes.
Kim's. So his lab is at 1:30. We can talk about it right then too, right after I go over the exam. I'll just stay right in that room. Okay?
Okay.
So we'll
Thank
see you
you.
then. Yeah. Anything else? All
No, that
right.
was my question.
Here, go ahead.
Thank you. No, that was my question.
That was your question?
I'll come to the chems group. Okay.
Okay. So we'll see you guys. It's 1:30, right? For Dr. Kem's lab?
Yeah.
All right. We'll see you then.